like the Fourier transform with a new parameter of S, which corresponds to a real part followed by the imaginary part. And this imaginary part is the frequency that causes the oscillation. And the real part here corresponds to a decay factor. So it's not this parameter e to the st is not a complex exponential anymore. It is a combination of a real exponential and a complex exponential. Perhaps something like this, with an envelope of a decaying factor, for instance, and in between there is an oscillation, something like that. So with this new parameter, we defined a new transformation called the Laplace Transform. And we said that there is the critical thing called the region of convergence, which defines many of the things. With this region of convergence, we may conclude what x of t is. Is it left-hand sided or right-hand sided? For example, we decide on that. And there may be more than one signal corresponding to the same Laplace transform x of s, and we have to take a look at the region of convergence to decide which one to choose. And for this region of convergence, we were looking at the so-called Laplace polynomials in the numerator and the denominator. Let's denote x of s as the numerator of s polynomial divided by the denominator of s polynomial. We said that the region of convergence is determined or bounded by the roots of the denominator, which are also called, we have roots from here, and they are also called the poles. But we didn't mention about the roots of the numerator polynomial. Let's consider our last example again that we have seen in the last hour, which was one of the last examples. Let's say, let's take a look at this one. X of t is equal to e to the minus 2t u of t plus e to the minus t cosine 3t u of t. And what was the Laplace transform for that? It was x of s. If you take a look at your notes, you will find this anyway. In its most compact form, it was this 2s squared plus 5s plus 12 divided by s squared plus 2s plus 10 and s plus 2. Here, in this denominator part, there were 3 roots. This is a quadratic formula multiplied by a linear form. And here, one of the roots is s is equal to minus 1. The other roots are complex, however. The roots coming from here are complex. It was minus 1 plus 3j and minus 1 minus 3j, as far as I remember. Okay, the roots of this quadratic form. So they were the poles. So the poles were minus 2, minus 1 plus 3j, and minus 1 minus 3j. Okay, these were the poles. But what's happening to the roots of the numerator? Does it affect anything? Does it have a meaning? It is not as critical as the roots of the denominator because it doesn't define the region of convergence. But it also has a name, and they are called the zeros of the system. And the zeros are the roots of this numerator of s, whatever they are, and wherever they can be. Usually, these are in the form of real polynomials. Therefore, the roots of the numerator are also in the conjugate pairs, in the form of conjugate pairs. They may be real. For this one, it's not real. So there we need to consider the roots of the numerator side as well. And they are called zeros. and the roots of the denominator are called poles. So the real or an alternative name of the S-plane is an alternative name for this one is also known as the pole zero pattern. Because on the S-plane with a real axis and an imaginary axis, by the way, this imaginary axis corresponds to the real part being equal to 0, so it is also known as the j omega axis as well. So I'm giving you alternative names to this one. This is also known as the sigma axis, another alternative name. So you can say like j omega and sigma axis, or real and imaginary axis. You can call it the S-plane, or you can give the diagram to with the name of pole zero pattern. And all you have to do is to indicate poles and the zeros on this plane, and indicate the region of convergence as well. Now, as we already know, the poles are very important. For example, for this question, the poles were like this one. And since the whole system is right-hand sided, it is to the right of the real part of these two poles, which is the same, greater than -1, and intersection with to the right of -2, coming from this root. So the region of convergence is simply to the right of -1. It was the answer that we already gave in the last hour. But you can also indicate the zeros here. I'm sorry that in this question the zeros are having some awkward values. It is the real part is slightly less than -1, and the imaginary part is slightly greater than 2 in magnitude. So the zeros are indicated with very small circles. Okay, that's the notation that we put. In order to have a complete S-plane representation or pole zero representation, you are required to put or indicate the poles as well as the zeros. You have to indicate them as well. However, the zeros may be inside the region of convergence. Inside ROC, you may have some zeros. It's not a problem. Okay, that's no big deal. So what are these? I mean, we usually, or in the books, it usually indicates, or the pattern is plotted like this. Poles with crosses, small crosses, and zeros with small circles. They are indicated like this. But they also have some important meaning. This whole plane has a meaning. It is, if you consider the magnitude of x of s in a magnitude form, what you really see when you take a look at this kind of an S-plane with arbitrary poles and some zeros, for example, like this. I'm deliberately trying to draw them in conjugate pairs to make it a reasonable S-plane diagram. So what do these points correspond to, and why are there some zeros, 0 points? What are we supposed to see here? Well, you have to imagine this as a surface. Okay, it's like a cake, an infinite extent cake, and you're looking from the top of that cake. And these points, crosses, are problematic because at those points the cake is exhibiting an infinite value. Because when you say that sigma is equal to this much and j omega is equal to this much, the S polynomial x of s diverges. It goes to infinity in magnitude. So these are the points with very sharp peaks of the cake. Or imagine it as a surface made of a stretched surface, a balloon, okay, a stretched balloon, and you put or you pull from one point, this point for example, and squeeze to extend to infinity. That's what's happening. to the surface of x of s. So these poles are the points where there are infinitely sharp and long spikes. How about these zeros? Then they are easier points. It's like this time you push the balloon so that its value touches to 0. So you press your cake, in other words. You make a cake and you press your cakes at these points and they go down to 0 at these points. So can you visualize what it may look like when you tilt the shape a little bit and try to look at it from an angle? These places will be going to infinity, and these places are the points where your surface touches down to 0. Okay, that's what it is, this S-plane. And the determination of the zeros is not very critical in terms of determining the region of convergence, as we have discussed, but in some cases the question, or in the problem, you may not see that some of the roots of the numerator and the denominator may be common. For this question, it's not. They are not common. We don't have a pole at an S point which is also the root of the numerator. There is no such thing going on here. But that is possible, and you may not see it at once. For example, you take a look at a quadratic polynomial or a cubical or a fourth order polynomial, and perhaps one of the roots is already -2. That is possible. You have to be very careful about that. In that case, you really need to make a simplification. This pole, in other words, may cancel a 0 at the top. The polynomial factorization may cancel each other. What does that mean? It means that there may be a 0 at this point and a pole at the same point, which may cancel each other. What does it affect? It affects the region of convergence, because you are eliminating a pole now by putting a 0 over there, and you're changing the region of convergence. Everything changes if a region of convergence changes. You have to be very careful about that, and in order to be careful, you have to find the zeros as well. Please do that. You really need to do it that way. And there may even be multiple poles or multiple zeros at a single point. The next example is with respect to that, like this. X of t is equal to delta t minus 4 over 3 e to the minus t u of t, and plus 1 over 3 e to the 2t u of t. Now, look at this. This is an expanding thing, exponential. It grows to the right-hand side. So there is a problem we have here, and this looks quite normal. Whenever you see some decaying exponential to the right-hand side, you may expect, and in the control systems courses, you will see that if your signal is like this, with a decaying exponential to the right-hand side, a decaying exponential to the right-hand side, etc., then it means that all of the poles are at the left-hand side of this. And what does it mean? What do we achieve by that? Since the signals are all right-hand sided, and if the poles are all at the left-hand side, then the region of convergence is to the right part of the rightmost pole, like this. And if all the poles are at the left-hand plane, then this j omega axis is included. That's good, isn't it? It means the Fourier transform exists. In the control systems, you will see, or you will remember, if you haven't already taken that course, and I hope you haven't, this is a very commonly encountered situation. They ask for stability of h of t. H of t. Is it stable or not? We were talking about this one as well, right? Stability is one of the topics that we covered. But of course, in control systems, it is the most important thing. One of the most important things. Is it stable or not? Now, if the Fourier transform of this exists, then we say that it is stable. Because otherwise, without the existence of Fourier transform, you cannot talk about the stability. So this is how you take a look at the stability now. If the Fourier transform exists, then it is stable. For right-hand-sided impulse responses, then all of the poles should be at the left-hand plane for the stability condition. And in the control system society, that's what they usually take a look at. They look at the poles and the zeros. If all of the poles are at the left-hand plane, that's a good thing. It means it's a stable system in terms of h of t, of course. But there is one condition where most of the control people just forget about, because they assume naturally. It is the right-hand-sidedness of the impulse response. Only if the impulse response is right-hand-sided, then the pole should be at the left-hand plane, so that this j omega axis is included. If it is not right-hand-sided, if the h of t is not right-hand-sided, then it may be perfectly the case that some of the poles may be here, and j omega axis is still in the region of convergence. Therefore, the system is stable. You can say that. But of course, physical systems are all impulse responses extending towards right. What does that mean? What is an impulse response extending to the right in terms of properties of systems? Causality or causality, whatever. I don't know the correct pronunciation of that. If it is causal, if the system is causal, then h of t is always to the right-hand side. And for that case, we need to have impulse responses with poles at the left-hand plane, so that j omega axis is included. Now this one, there seems to be a problem. This will make, since it's a decaying exponential, it will make a pole at the left-hand plane. The pole is, I can clearly say that the pole is at where? At -1. At -1 there's a pole. Here this one has a pole at 2. Clearly we will find it. There is a pole at 2, there is a pole at -1, and they are all right-hand sided. So if there is a pole at -1 and if there is a pole at 2 and everything is right-hand sided, then the region of convergence must be to the right of 2. And does it include the j omega axis? No. Therefore, we say that if this is an impulse response, somehow, not x of t, but h of t, in other words, then it will be an unstable system. And we can see that instability from here as well. We apply an impulse, and the impulse response is blowing up as time goes to infinity. So this is an unstable system if it is a system. But now, what is the Laplace transform is another issue that we need to resolve. These two we already know. This one, what is the Laplace transform? For that, I would like you to take a look at the Fourier transform. What was the Fourier transform of delta t? 1. It was 1. The Laplace transform is the same, because we have the same exponential term. So the Laplace transform of this is 1. The Laplace transform of the others are -4/3, 1/s plus 1, plus 1/3, 1/s minus 2. This is the Laplace transform expression. So x of s is equal to, there is a 1 term here as well, and it will complicate things a little bit. It will be like this: s minus 1 square divided by s plus 1, s minus 2. So this is the Laplace transform that we have. By taking a look at that Laplace transform now, it's also possible to put the zeros, not the poles only. The poles are at -1 and at 2. Where are the zeros? They are at 1. How many zeros do we have? 2 zeros at 1. And we draw it with 2 small circles within each other like this, for example, at 1. Okay, that's the notation for indicating a multiple zero. If you have a multiple pole, you just put crosses quite near to each other as well. Now, all of the questions that we have seen were easy. They were all in real exponential or complex exponential forms multiplied by u of t's, or there is a delta t. So for most of these questions, we already have the Laplace transform, and we are just combining polynomials. But in some cases, we don't really come up with polynomials. Let me ask you a difficult question. X of t is equal to e to the minus at for time duration from 0 to capital T, a finite duration of time, and 0 else. Now, what is the Laplace transform of this one? It's not e to the minus at times u of t, in other words. It is something else. Okay, there is a difference. How are we going to solve this? You can solve it in several ways. You can do it like this times a u of t minus the same thing times u of t minus capital T, for maybe, for example, an approach to solve this question. But let's try to solve it directly using the integral x of s is equal to this integral. We will have x of t, but x of t is valid only from 0 to capital T. So let's not start from minus infinity to go to plus infinity. X of t is already within this range. And within this range, the signal is e to the minus at, and the Laplace kernel is e to the minus st dt. So we need to take this integral, in other words. And this integral, if you evaluate, will be equal to 1 over s plus a, which is something expected because without this interval only, if it is from 0 to infinity, this would be the Laplace transform. But it's not only 1 over s plus a now. It is this times 1 minus e to the minus s plus a capital T. We have an extra term. Now, without going into any further simplifications and taking a look at the poles and the zeros, okay, of this system, this whole system, we have to analyze it, of course. But by just looking at this signal itself, I can safely claim that the system should not have any poles. What do I mean with that? And how do I know that? I know it because it satisfies two conditions. First, it is a bounded signal. It is not extending to infinity, from minus infinity to 0 or from 0 to infinity, whatever. The extent of the signal is finite, and within that finite interval, the values are also finite. So it's a signal starting at some point, ending at some other point, whatever that signal may be. This, for example. The Laplace transform of this one will not have any poles. I assure you that. So be careful when you are answering questions in the examinations, for example. Draw the poles and the zeros, for example, I can say. You have to say that there is no pole. If there is no pole, what is the region of convergence then? We will come back to that question. Because the region of convergences start from poles extending to the right or to the left. Is it a right-hand sided or a left-hand sided signal? Neither. It's just a finite extent signal that has to be considered by itself. Now let's take a look at the poles of this system. Where is the pole? Can you see a pole here? Of course, there is a denominator, and it says that s is equal to minus a is a pole. Right? But look at the numerator now and put s is equal to minus a. When s is equal to minus a, minus a plus a is 0, so it becomes e to the 0. What is e to the 0? 1. 1 minus 1 is 0. So from here, I find that s is equal to minus a is a 0 as well. So since it is both a pole and a 0, they probably cancel each other. But we know that the strength of the roots in the numerator and the denominator may also be different. For example, if I say s minus a to the power 3 divided by s minus a to the power 4. Okay? Here we have a pole at s is equal to a, and we have a 0 at s is equal to a as well. They seem to cancel each other, but up to what extent? 3 of the zeros will cancel 3 of the poles, and there will still be a remaining pole. And this will still cause the fact that s is equal to a will still be a pole. They may not cancel each other completely. You have to take a look at how strong the poles and the zeros are. Well, it is safe to say that the strength of this pole is only 1, and if you just cancel it with 1 0, this will be cancelled. But is there another probability here, or are there another zeros? S is equal to a, minus a is a 0. Are there other zeros as well? For that, it is safe to take a look at, this is x of s. What is x of s at s is equal to minus a? We have to take a look at that, and it looks like a 0 over 0. It's ambiguous. We don't know the value for that. What do we do if there is an ambiguity, uncertainty of 0 over 0? Apply the Hospital's rule, which is the derivative of the numerator of s divided by the derivative of the denominator of s. This is what you have to take a look at, which is the Hospital's rule. In other words, is s is equal to minus a 0 or a pole or something else? Are they completely cancelled? That's the thing that we're looking for. And here that is equal to d by ds of 1 minus e to the minus s plus a t divided by d, well, whatever, d by ds of s plus a. And the answer to this one is, of course, evaluated at s is equal to minus a. You have to evaluate this expression at s is equal to minus a. And that is equal to t times e to the minus a capital T times e to the minus st evaluated at s is equal to minus a. And when you do that, when s is equal to minus s will be a, and this will be e to the minus at e to the plus at, which is 1. So the whole expression will be equal to capital T. So at this point, we conclude that at s is equal to minus a, there is not a 0, there is not a pole, there is some value. The pole and the 0 are cancelling each other, and we obtain a finite value, a non-zero and finite value of capital T. Okay. So this is something that you have to be careful about. Now let's see another example. In this example, we have x of t to be equal to e to the minus b times magnitude or absolute value of t. What do I mean by that? This is a two-sided signal, and we found the Fourier transform of this one previously as well, if you remember. That is e to the minus bt u of t plus e to the bt u of minus t. It's the right-hand sided and the left-hand sided combination. Can you see that the shape of this signal, depending on the value of b, if b is greater than 0, then it will be a decaying exponential to both sides. However, if b is less than 0, then it will be a growing exponential at both sides. This is b greater than 0 case, sorry, b. And this one is b less than 0 case. Obviously, if b is equal to 0, then x of t will be 1, and we have to consider it separately. Now let's think of these two cases for the time being. This part, e to the minus bt u of t, seems to have a Laplace transform of 1 over s plus b. And this part will have a Laplace transform of minus 1 over s minus b. And the regions of convergences of the two are different. The first one has a region of convergence like this. Real part of s, or sigma, is greater than minus b. Why? Because there is a pole at minus b and it is right-hand sided. Where is the pole of this one? 1 over s minus b. It is at s is equal to b. And it is left-hand sided, so we say the region of convergence for this part is the real part of s is less than b. Now what is the intersection of the two? If b is positive, let's assume a positive b somewhere here. Let's assume this is b. And this is naturally minus b. It is less than b and greater than minus b. So it's the intersection of the two which produces some stripe like this between minus b and b. That is the region of convergence. Does it include the j omega axis? Yes, it seems to be right in the middle, which is the j omega axis. That's why for positive b, or for this signal, we have a Fourier transform. In fact, we found the Fourier transform for that, right? It was one of the examples that we have seen. How about the other case? Suppose that b is negative, then b is here. And then minus b will be positive. This will be minus b. And look at the regions of convergences. It is greater than minus b, which is here. And it must be less than b, which is here. What is the intersection of the two sets? It's an empty set. Right? So if b is less than 0, then the region of convergence is an empty set. Which means we don't have a Laplace transform for this signal. In many cases, if the signal is growing at both sides, at two sides, it is probably not possible to find the Laplace transform. The Laplace transform doesn't exist. The region of convergence will not have any region. It will be an empty set. This is an example of that. The other one, if it is decaying at both sides, the Laplace transform usually exists, but if it is two-sided like this, then extending at both sides, we expect a stripe, something like this, between two poles. We expect a region of convergence between two poles. Why? Because the right-hand sided convergence, or the right-hand sided decaying exponential, will correspond to a pole and to the right of it, the other one will correspond to another pole, and to the left of it, their intersection must be between two poles. So it will be a stripe, the region of convergence. All right. Now, the chapter in the chapter of Laplace transform from the book of Oppenheim, it also gives you the theoretical inverse of the Laplace transform. Okay, there is an inversion formula. I don't remember I have ever mentioned about the inverse Laplace transform formula. Okay, you remember that? No. We only wrote down the Laplace transform. We said x of s is equal to this integral from minus infinity to infinity, x of t e to the minus st dt. And I have never indicated what x of t is in terms of x of s. But we do have an inverse Fourier transform. So if the inverse Fourier transform, or if the Fourier transform exists, or in other words, if your j omega axis is included in the region of convergence, the best way to find the inverse Laplace transform is to apply the inverse Fourier transform. The easiest way. That's the formula. But suppose that the j omega axis is not included inside your region of convergence. Then what are you going to do? You cannot even talk about a Fourier transform. Without the Fourier transform, how can you take the inverse Fourier transform? That may be a problem, but for that case, what you really need to do is you have to find the inversion like this. Here you need to write x of s, but I'm going to write it like this: sigma plus j omega and e to the j omega t d omega. Instead of ds, I'm writing it in terms of d omega. And this formula is the same as the inverse Fourier transform, almost, except for the fact that I'm not writing it as x of j omega, but I'm writing it as x of sigma plus j omega. So originally it was this, but now I'm writing it like this. What is the difference between the two in terms of theoretical calculations? The difference is as follows. Normally, the inverse Fourier transform is an integral of this x of j omega times e to the j omega t d omega, which is the integration along the j omega axis. Along here, along this axis, you integrate. If that axis is not in the region of convergence, you have to find the sigma which stays inside the region of convergence. Suppose that the region of convergence is here. So you find the sigma value and you integrate along this line. Instead of along the j omega axis, you integrate along this line. By changing omega, of course, you are varying in terms of omega, but the value of x of s is not integrated as j omega, but it is evaluated at capital X of sigma plus j omega, which is inside the region of convergence. Now I'm telling you this integration just for some cultural purposes, okay, for your information, because you never do that. It's not there is not a practical way to find analytically this integral along a path like this. It is just an information. The correct way of doing it is either by knowing the inverse Fourier transform if j omega is included, or by knowing the answer. If you know the pairs, this x of t has this x of s, if you know them. For example, for exponentials like this one or like this one, we already know the Laplace transforms. So by looking at the Laplace transform, if the Laplace transform is the combination of the two. By the way, we haven't combined these. What's the combination of them? Let's also write down the answer. The answer is minus 2b over s square minus b square. So if you encounter something like this, you know that its inverse Laplace transform will be this. Or if you encounter something like this, a first order system, then its inverse Laplace transform would be this, depending on the region of convergence, of course. So that's the way, that's the systematic way to find the inverse Laplace transform. Never try to take this integral without any prior information. Okay. Now the last thing for today is with respect to the Fourier transform evaluation from the Laplace transform, because we know that if j omega is in region of convergence, then x of j omega is equal to x of s evaluated at s is equal to j omega. We know this. Now this knowledge will give us a strong information about how to determine the magnitude of x of j omega. Of course, everything works only if j omega is inside the region of convergence, and the angle of x of j omega. What are they? How can we discover these things? Now, the way to discover them is as follows. You take a look at the pole zero pattern. Suppose that you have some poles here and some other poles here as well. Some zeros and some more zeros, like this. For instance, I'm just drawing something arbitrary. Now what I'm trying to take a look at is, along this j omega axis, I will evaluate the magnitude. It's the magnitude of the cake. Do you remember the cake shape? The cake was going to infinity at these pole points, and they shrink down to 0 at these 0 points. You remember that? Now I'm cutting the cake from here using a knife. I cut the cake and I take a look at the profile of that cake. Okay, the cutting profile. For example, if there is a 0, let's also put a 0 here. If there is a 0 along the j omega axis, I know that the cake will go down to 0 in the profile, which is the magnitude of x of j omega. Okay, that is the profile of the cake that I'm looking at. If there is a pole at the j omega axis, then that means there are some strong spikes going to infinity for the magnitude of x of j omega. But what happens if they are near to x of j omega, or they are far away from x of j omega? As they are nearer to x of j omega, the magnitudes will be larger. As they are far away, or if the zeros are nearer to x of j omega, then the magnitudes will be smaller. That's the expectation. Let's take an arbitrary point of omega. Suppose this is omega 1. This omega 1 point is an example omega, and the magnitude of x of j omega at omega is equal to omega 1 is equal to a constant. We don't know that constant. For that constant, you have to take a look at the original expression itself, but it's just a scale. Apart from the scale, the shape doesn't matter. It's just being scaled, in other words. You first measure the distances to zeros. How many zeros are there? 5 zeros. So there are 5 distances to zeros. And those distances are indicated by, let's call them dz1, dz2, dz3, dz4, and dz5. I'm multiplying their distances. The Euclidean distances, you just need to measure the distance from omega 1 point to here and multiply them, divided by how many poles are there. There are 4 poles. You measure the distance from this omega 1 point towards the poles, and they are dp1 d times dp2 times dp3 times dp4. As you see, these distances will change as I change omega 1, right? Just take a look at these distances and drag this using a mouse if you wish, and push it upwards or pull it downwards. The distances will be changing. So as they change, we come up with an x of j omega shape. In magnitude. Let's see an easier example. Suppose we have 2 poles here, a 0 here, a 0 here, and a 0 here. Can you guess what x of j omega would look like? Around here, the distance between this point, for example, and this 0 will be very small, and it's in the numerator. So it will become smaller and smaller. I will probably get some shape like this around 0. And it will exactly touch 0 at this point. But as you see, as I come nearer towards this pole, this time the distance between this point and this pole will be very small, and it's in the denominator, in the multiplication form. So the magnitude will be larger. And then after crossing this point, if you go upwards, you will get farther away from here, and you will become nearer to this 0 this time, and therefore it will be going down to 0. And the similar situation will be symmetrically happening in the left hand side. And after that, it will first increase and then decrease back to 0. Increase and decrease back to 0. Why are they decreasing back to 0? Because the number of zeros is more than the number of poles. If the number of zeros is more than the number of poles, as you extend to plus infinity or minus infinity along the frequency axis, the distances for, at the numerator, sorry, I'm doing just the opposite way. It will extend to infinity. Excuse me about this, because the number of zeros is more. The numerator multiplication will be more than the denominator multiplications. How many distances will there be in the numerator? There will be 3 distances to these 3 zeros, and there will only be 2 distances in the denominator, so they will go to infinity as omega goes to infinity. What could you do in order to suppress these tails? For example, you could add, for example, 2 more poles here, which are quite far away, but the number of poles is now larger than the number of zeros, which will cause them to go back to 0 after some point, like this. If you do it that way, suppose that we have these 2 poles as well. What is the design outcome? What did we design? What is this? What does it look like? It looks like a bandpass filter or bandpass system. Okay. Can you relocate these poles and zeros differently in such a way that you can have a low pass filter, you can have a high pass filter, How can you do that? How can you design them? That is just by putting poles and zeros. Luckily, again, if you take a look at the applets, there is an S-plane applet where you insert poles and zeros with your mouse deliberately. And you can even move them, drag it, and then move it. And it simultaneously shows you this figure. And you can see how it changes as you move this towards here, etc. Or put an extra pole, put some extra zeros somewhere else. What does this shape look like? The applet is a very nice one. And furthermore, if you drag a point along this axis, for example, if you drag here, it shows you the distances and illustrates this phenomenon as well. All right? So please run that applet and try to design a low-pass filter, a band-pass filter, a high-pass filter, a band-reject filter, for example. That is also possible, just by locating some poles and zeros. Why am I asking you to do it? We will see some more examples in the next week as well about this. We will make more illustrations, but until next week, please do that, because what I do in the exams is usually something like this. I use that applet and take screenshots of this and this, several screenshots, and then I cut them and shuffle, just like the question in the second midterm. 1 is related with B, 2 is related with C. Okay, which corresponds to which? How can you solve that? You can only solve it if you have already seen it in the applet. Okay, so run the applets, please.